It's my honor to give your first colloquium of this academic year. It's my first time at the CCA. It is an amazing place. I'm really jealous of y'all. So I come from South Bend, Indiana, where we don't have food. And so the fact that you can just like order food from any amazing place that you want, it's paid for you, is just like surreal to me. So good for you, good for you. So I want to tell you about the Subaru Prime Focus Spectrograph, specifically the Galactic Archaeology Survey. And a lot of the work that I'm presenting here is the work of two really awesome people. Roman Gerasimov is a postdoc at Notre Dame, is a Society for Science Fellow at Notre Dame. And László Dobos is a professor at I don't know how to pronounce it, Eötvös Loránd University in Hungary. And both of them have done heroic efforts in getting the Galactic Archaeology Survey for PFS going. We're also honored to have Rosie Wise, who is a co-chair for the Galactic Archaeology Working Group, visiting for the day from Johns Hopkins. And Carrie herself didn't mention, but she is also a very, very important person in the Galactic Archaeology Working Group. So I want to tell you first about the PFS instrument. There's a lot of cool things that went into building this instrument. It has an enormous number of fibers over a very large area for an 8-meter telescope, but I'll get into that in a moment. Then I'll tell you about the science case for PFS Galactic Archaeology. And just to be clear, when I say PFS, I'm talking about the Prime Focus Spectrograph. I'm not talking about a point spread function. Everyone says that, you know, the PSF instrument. It's not the PSF instrument. It's just a very poorly named spectrograph. So the Prime Focus Spectrograph is what PFS stands for. And then finally, I'll tell you about our first observation. So we actually began our 6-year survey, you know, like the Enterprise went off on a 5-year mission. We're now embarking on a 6-year mission to observe 3 major science cases in the universe, the nearby universe. And I want to tell you about our very first observations that we conducted in March of this year. This little dog here is actually my dog. So I gave ChatGPT a picture of my dog and I asked it to make a picture of her pondering the universe. This is what it came up with. And so you'll see a few ChatGPT renderings of my dog for this talk, and they get progressively more hilarious. So the PFS collaboration is truly a worldwide collaboration. We span something like 7 countries, and each of them contributes something unique to the project. Japan is the originator of this project. They provided the telescope and the observatory. Hawaii, not a country, but Hawaii, part of the US, is where the observatory actually is, on the big island of Hawaii. Lots of different affiliations in the United States. Notice that Notre Dame is not one of them. It's just really me at Notre Dame. Brazil provided the fiber cable that connects the prime focus all the way down to the spectrographs. France provided the spectrographs themselves. The Max Planck Institute provided an enormous amount of software, especially the fiber positioning software. China is providing lots of, well, money and also some scientific expertise. And so this is truly a worldwide collaboration. It's hundreds and hundreds of people. And the collaboration meetings are always interesting. So the overview of the instrument itself is that really, it's more than one instrument. It's really like 3 instruments in one. And so I want to go through each one of these instruments one by one. The first one I want to talk about is the Prime Focus Instrument, PFI. So this is where like the most exciting stuff is, if you ask me. So the light from the sky reflects off the primary mirror and then into the prime focus. That's what the prime focus means. You only have one reflection off of the primary mirror. But there's also an instrument that sits in the Cassegrain. You might be like, wait, why is there an instrument that sits in the Cassegrain if there's not a secondary mirror? I'll get into that. And then there's also the spectrographs themselves. The cool thing about the prime focus instrument is that it puts 2,394 fibers all at the prime focus of the Subaru telescope. And so the PFI instrument itself is about this big. So it's not quite as tall as me, but it takes up the full prime focus of the Subaru telescope. And it's really cramped up there, actually. In fact, Jim Gunn actually designed the calibration lamps that work for the PFI, but because this thing is, like the dome is right here. And so to have the calibration lamps actually work, he actually had to design this not even parabolic thing that actually projects a flat field onto the dome, even though the dome is like right here above the prime focus instrument. So it's really, really cramped up there. It's a pain in the butt to take the PFI on and off the prime focus, because this instrument is not permanently mounted on Subaru. It trades places with the secondary mirror and with the Hyper Supreme Cam that also sits at the prime focus. And so this thing has to come on and off. It's a big operation, but they managed to do it in an afternoon, which is pretty impressive. So another cool thing that hangs off the prime focus is the wide field corrector. So there's a lot of optical aberrations at the prime focus. In order to correct for them, you need a lot of lenses in the way to correct for all those optical aberrations. A cool thing about the prime focus, the wide field corrector, is that it was built by Canon. So if you have like a Canon DSLR camera, same company that built this thing. So you can imagine this is like a telephoto lens, although you wouldn't want to hang it off your DSLR because you wouldn't be able to pick it up. It literally weighs a ton.
Is there AO systems?
Go ahead.
AO system.
For the PFS, there is not an AO system. Subaru Telescope does have an AO system, but it sits on the floor of the telescope, of the observatory dome. There's no AO for PFS itself, no. So there are different instruments that have different science cases that have much, much smaller fields of view for AO. Now, the way that the fibers work is they're much, much smaller than the total collecting area of the fibers is much, much smaller than the total patrol region that they patrol around. And so we have to be able to position the fibers on the particular stars or galaxies that we want to observe. And the way this is accomplished is with these devices that for some reason are called Cobras. I never quite got this until I was actually giving a similar talk, and someone said, well, it's because they like a snake, like a cobra. I don't know if that's true. Do you know if that's true, Rosie? Like why they're called cobras? It's because they look like this. Okay. And I was like, oh, that's why it's called that. But really, this thing is about the size of a ballpoint pen. And a ballpoint, I don't have a ballpoint pen. It's actually a good analogy because they have a little cap, you know? And so you can imagine that this axis of the ballpoint pen is spinning, the major axis of the ballpoint pen is spinning, but then the cap that sits on the end of it can also spin independently. So it's like a turntable with an arm hanging off of it. And so with these two axes, which we call the theta and the phi axes, the tip of the fiber, which sits here, can patrol this entire patrol region. This entire patrol region, when projected on the sky, has a diameter of 107 arc seconds. And so these things are positioned side by side, as I'll show you on the next slide. And the fiber tip itself, it only has a diameter of 1.1 arc seconds. So if you're used to like Sloan aperture effects, like Sloan fibers, this is a significantly smaller area on the sky. We still have aperture effects, but they're much smaller than the Sloan fibers would be. Now, this thing is, again, the size of a ballpoint pen, and the motor that controls the phi axis is this little tiny piezo motor right here. This little tiny piezo motor, this is somebody's finger. And so this little tiny piezo motor is like what controls this thing. And so, as you can imagine, these things sometimes break. And so we actually do have broken fibers, and so they just sit there and we're not able to move them. But fortunately, there's not too many of those. Now, these patrol regions overlap each other. And when you put them all together, all 2,394 fibers, they tile a hexagonal area that covers 1¼ square degrees in the sky. Now, this is impressive for an 8-meter telescope. Now, if you're thinking of other wide field spectrographs like DESI, they have significantly larger collecting areas, but they're not on an 8-meter telescope. So this is a really impressive field of view for such a large telescope. Now, the other thing that I want to mention is this: there's an instrument that actually sits in the Cassegrain. Why? Why is there an instrument that sits in the Cassegrain when there's already an instrument that's not reflecting any light in the prime focus? Where is the light coming from that it looks at? Well, these little piezo motors aren't very accurate. If you know what a piezoelectric device is, it just kind of vibrates when you put a voltage across it. And so this vibration isn't very accurate. So when you tell it the fibers to go somewhere, they don't really go there. You have to iterate multiple times. So you have to command the motors to go to the place you want to go and then see where they actually went. So we back illuminate the fibers. And then if you're at the Cassegrain focus looking up through the hole in the primary mirror, what you see is a little constellation of fibers at the prime focus. And you can measure very accurately what their true positions are, and then command deltas until they get within a certain tolerance of where they need to be. And so the metrology camera, which sits in the Cassegrain focus, is looking up at all these things. And so what it does is it positions the number 1 fibers, then the number 2 fibers, then the number 3 fibers. And after about 6 iterations, and the fibers are within their right tolerances where we expect them to be, within 6 plus or minus a couple iterations. And this iteration is quite quick, actually. You could complete a full alignment in less than 40 seconds. Which it sounds like it's not very precise, right? Like you're commanding these not very precise motors and they don't really go where you want to go. But you can align them to within the desired tolerance in 40 seconds. That's a lot faster than, say, like another spectrograph that I'm fond of, DEIMOS on the Keck telescope. There you have to like put the grading in 0 with order, take a direct image. That whole process takes 5 minutes. This is done in 40 seconds, so it's pretty nice. And then finally, the actual science gets done at the spectrographs. I didn't actually call out the fiber cable itself, but that itself is its own instrument. It's an 80-meter long cable that's carrying well over 2,394 optical fibers, because there's also these fiducial fibers and all sorts of other stuff that this cable is carrying. This cable gets connected and disconnected every time the prime focus instrument comes on and off the telescope. It's a nightmare, but somehow it sort of works. And so this 80-meter long cable is carrying all this light down to the spectrographs. And when the Alt-Az telescope rotates to track the sky, the cable has a cable rat. It goes through the same cable rat that all the other electronic cables go through for the telescope. Now, when the light gets to the spectrograph, it's split up into one of 12 spectrographs. So there's 4 identical systems that look like this. And the reason is that we couldn't build a single spectrograph that could accept all 2,400 fibers. And so we build 4 spectrographs, each of which accepts 600 fibers. And then to maximize the efficiency across a very wide wavelength range, we do what all spectrograph designers do. You split up the light with dichroics into different channels. And the different channels we have are a blue channel, a red channel, and an infrared channel, which for some reason is purple. And so the light comes in through an entrance slit. So the fibers are all directed into this entrance slit here. They get collimated, as you do with the spectrograph. And then the dichroic light reflects the blue light and transmits the red light. And then this is a dichroic with a redder cutoff, reflects the red light and transmits the infrared light. Each of the 3 spectrographs is similar in design. Did I show? Oh, I didn't actually show it. Oh, yes, I did. So the 3 similar design spectrographs have a VPH grading, a volume phase holographic grading. And so this is sort of like a diffraction grading, but instead of having a reflection diffraction grading, it's a transmissive refraction grading. The grooves are not physical grooves carved into a piece of metal. Instead, they're grooves that are holographically carved with lasers into a transparent medium. And so what that does is it allows the light to diffract. It goes through this pretty complex spectrograph that has got to be pretty compact, but also tries to minimize the number of reflective surfaces. And so this is a spectrograph that rarely uses what's something called a Mangeant mirror. And if you're an instrument nerd like me, then a Mangeant mirror is actually 3 optical surfaces in one. What it is, it's a refractive element, so it's a lens, but it's silvered on the back. And so the light goes through the lens, reflects off the mirror that's on the back, that's painted onto the back of the lens, and then comes back through the lens again. So it's 3 optical elements for the price of 1, and it's not a cheap price. And then that Mangeant mirror refocuses the light onto the detector. So the detectors sit right here. Importantly, this is what's called a Schmidt spectrograph. And so a Schmidt spectrograph, the detectors are actually hanging in the middle of the beam. And so this is actually a choice for the way that we would have to have a compact design. The Schmidt spectrograph has a short F number, but unfortunately what it means is there's a large central obscuration in the beam, so that actually cuts down on our efficiency a little bit. And so when the light is actually dispersed into a spectrum, we have 3 channels. Remember, the blue channel, the red channel, and the infrared channel. Now, the red channel has 2 different modes, a low resolution mode, LR, and a medium resolution mode, MR. The low resolution mode is contiguous in wavelength coverage with the blue and the infrared arms, but the medium resolution mode is pointed at the same detectors with the same number of pixels. And so with a higher resolution, we're not able to get as wide of a wavelength coverage. The medium resolution mode is used exclusively by the Galactic Archaeology Working Group. And the main reason for that is we want to be able to get high precision radial velocity. Well, I shouldn't say high precision in a crowd that actually has exoplanet people. And want to get higher-ish precision radial velocities for faint stars. So the actual line spread functions, our full width half maximum of the lines ranges from 2.7 angstroms for the medium resolution mode, 1.6 angstroms. And this is an either or thing. You can't observe with low resolution, medium resolution at the same time. You actually have to change out which VPH gradient is inside of the medium resolution spectrograph. Now, the typical throughput of the system isn't like super impressive for spectrographs, and that's partly because of the Schmidt camera design, but it tops out around 30% for the LR mode for the red channel. Now, the survey that we just embarked upon is called a Subaru Strategic Program, SSP. So the Subaru Observatory has done a couple of these things so far, the most famous being the Hyper Supreme Cam SSP. It's a big survey of extragalactic structure in the universe. The PFS SSP was approved a year and a half ago for 360 nights over 6 years. And the SSP, the way we designed it, was 3 different science pillars. There's a cosmology science pillar. They're doing a bunch of cool stuff. I'm not going to talk about it very much at all. I just want to say one really cool thing that they're going to do. They're actually attempting to measure the mass of the neutrino with a telescope, which is really cool. And the reason is that if there's, okay, very briefly, there's 3 neutrinos, right? We know that 2 of them are kind of similar masses and the other one's not. So there could be in a normal mass hierarchy where you have 2 light neutrinos and 1 heavy, or an inverted mass hierarchy where you have 1 light neutrino and 2 heavy. If the mass hierarchy is inverted, then the sum of the neutrino masses is large enough to actually have an effect, a measurable effect on the large-scale structure of the universe. And so by doing this large-scale structure survey, especially using the near-infrared arm that can get out to higher redshifts than if you didn't have it, then you're able to actually see if this thing is there. This is just one of many things the cosmology group is trying to do with the Prime Focus Spectrograph. The Galaxy Evolution Survey is exactly what it sounds like. It's a bunch of different projects trying to map the evolution of galaxies from low redshift to high redshift. But I'm going to spend the rest of the talk talking about galactic archaeology. What are we going to do with that? So here I asked ChatGPT to make my dog a galactic archaeologist. It had no idea what to do with that, so it decided to make her look like Indiana Jones and put a galaxy behind her. So the 3 things that the galactic so I mentioned that PFS has, the SSP has 3 science pillars. Well, galactic archaeology itself has 3 major science cases. One of them is the disk and the halo of the Milky Way. I'll talk a little bit about that. Another one is what can we do with dwarf galaxies? We can do things involving the dynamics, and we can do things involving the chemistry of stars and dwarf galaxies. And finally, our nearest neighbor galaxy, M31, our nearest large neighbor galaxy, M31, aka Andromeda. For those of you who are of a certain generation and had a MacBook, you recognize a picture of Andromeda, although for some reason they decided to Photoshop out M32 because they thought it was ugly or something. So if you're looking at that, it's like, hey, my MacBook didn't have that galaxy in this because, I don't know, whoever designed the background for Mac decided to Photoshop out M32. The co-chairs are Professor Masashi Chiba at Tohoku University, Rosie Wise, and me for the Galactic Archaeology Working Group. So our survey plan is that we're going to be spending roughly a third of the time on each of these cases, not quite a third of the time, but roughly a third of the time. We plan for 91 clear nights total. How do we know the nights are going to be clear? We don't. We actually have 130 nights dedicated to the survey, and with an assumed weather factor of 70%, meaning 70% of the nights are clear, which is typical for Mauna Kea. Then we get 91 clear nights out of those 130. We decided to devote about 27 of them to dwarf galaxies. Almost all of those nights will be devoted to 5 classical dwarf galaxies plus 1 ultra-faint dwarf galaxy. And so for those of you who know these names, Fornax Sculptor, Draco, Sextans, Ursa Minor, and 1 ultra-faint dwarf galaxy, Bootes 1. One of the cool things that we have, and I'll get into a little bit more, is the fact that because we're on Subaru, we're also making use of the Hyper Supreme Cam pre-imaging for these galaxies. We've pre-imaged most of these galaxies with HSC's Hyper Supreme Cam's narrowband filter centered on the magnesium triplet. And I'll tell you why that's important a little bit later. We're also spending just one night on an isolated dwarf irregular galaxy. This is my little pet case, NGC 6822. The Milky Way, we're going to have several different fields in the Milky Way that we're looking at. So we're looking at the outer halo of the Milky Way across multiple sight lines, and I'll show you why those sight lines in particular are chosen near the end of the talk. We're looking at the disk halo interface of the Milky Way and turnoff stars, and we're looking at streams, particular streams in the Milky Way, those 4 streams, if you're into that, Adrian. And then also M31, we have a lot of nights devoted to that as well. 32 nights we're going to be devoting to M31. So what our pre-selection there is again based on this narrowband selection to sort out dwarf stars from giants that are actually members of M31. And also we use PANDAS pre-imaging. So PANDAS is a CFHT survey using CFHT megacam that mapped out a huge area around M31. So we decided to make use of that. We added on our narrowband selection from Hyper Supreme Cam, and together we have the imaging that we were going to use to select targets in M31. So to give you an example of the power of PFS, I'm showing you a picture of the largest of the intact classical dwarf spheroidal galaxies. I have to be careful with my language. The largest of the intact classical dwarf spheroidal galaxies, Fornax. I think that's right. Yes, because it's not, if the Magellanic Clouds are not considered dwarf spheroidals, and Sagittarius is not intact. Okay. All right. So this is a picture of Fornax, and you might be thinking that this is Fornax, and you'd be right, but this is just the center of Fornax. So I don't know if the lights in here are too bright, but can you see there's like an extra fuzz there? So that is the core of the Fornax dwarf galaxy. But a lot of these stars that you see out here, especially the really, really faint stars that you see out here, are also members of the Fornax dwarf galaxy. Now, whenever we look out of the Milky Way, we have to look through the Milky Way, which means that almost all of the stars that you see out here that your eyes are drawn to, the bright stars, those are not part of Fornax. Those are foreground stars that are right in front of our faces in the Milky Way. It's the little tiny faint ones behind the foreground stars that are members of Fornax. Now, how do we figure out which of those stars are members and which of the stars aren't? Well, first of all, we're going to get spectra, so we'll be able to measure which velocities there are. But we also have a way to pre-select the members to spend our precious fibers. That's the narrowband selection I'll talk about later. Now, I want to be able to measure the stars that are way out here in addition to the stars that are in here. Why? Well, first of all, the center of the galaxy has been done. It's old news. We know what the center of the galaxy looks like. I want to measure the stars out here for a whole host of reasons. One, some of the most interesting stars are out there because of the dynamics. And so if you can measure the velocity dispersion profile of this galaxy, and not just the velocity dispersion profile, but the full line of sight velocity distribution of this galaxy at different radii, you can learn something about the shape of its density profile, the shape of where its gravitational attraction is. And that can tell us something about dark matter. I'll get to that in the next slide. But also, there are weak but noticeable radial metallicity gradients in these galaxies. And the oldest, most metal-poor stars are most likely to be found in the outer regions. They're probably not hanging out in the center. They're probably hanging out in the outskirts of the galaxy. So if you want to find the most interesting stars, you kind of have to do a wide area survey to capture the rarest stars in the galaxy. The problem with doing a wide area survey is, this is my previous favorite spectrograph, Deimos. This is the field of view of Keck Deimos. You can put about 120 slits, not fibers, but it's an imaging spectrograph. So you cut slits in a slit mask. And that's about the field of view of Deimos. But remember, the Fornax members go off the edge of this projector here. So we want to be able to image the stars that are way out here. And if I were to be able to do that with Deimos, I'd have to tile this entire area with Deimos. It would take like a year of Keck time. And even at Caltech, they wouldn't give me that much time. Here's what the flame spectrograph on the VLT looks like. Now, Fornax is in the southern hemisphere, so you can see it with the VLT. So flames can also see it. But Flames only has 130 fibers. They're distributed over a wider area than Deimos, but it's a lot sparser sampling. And also Flames has a limited spectral range. With PFS, you get spectra from 3,000 angstroms all the way out to 12,000 something angstroms, all at one shot with 2,400 fibers over 1¼ square degrees.
That's about a few hundred parsecs across. What is that? A few hundred parsecs?
You're asking what is the projected size from
A few
one?
hundred parsecs, roughly.
Let's see. The distance to Fornax is 80 kiloparsecs, and this is 1¼ degrees across. Oh my goodness, how many projected parsecs is that? It's hundreds of parsecs. Yeah, you were quite right, Nicola. Did I do that right? I think I did that right. So with just a couple of PFS points, it's more than a couple. With I think for Fornax, we're doing 12 PFS pointings. Each one's going to last 3 hours times 2, and I'll tell you why times 2 in a moment. We'll be able to cover the entire area within the tidal radius of Fornax. And so this is the power of this instrument. It's wide area and an enormous multiplexing factor. How many fibers can we put on these galaxies? So what are we going to answer with these questions? So one of our big headline science questions is, what is the nature of dark matter? And this has to do with a problem that's quite famous called the cusp core problem, or what is the inner slope of the dark matter profile. So if you run a dark matter only cosmological simulation, you get these cuspy profiles, these NFW profiles that have a steep profile in the center parts of the galaxies. But it turns out that when you go out and measure the density profiles of actual galaxies, they don't all seem like they have cusps. Instead, they have what looks like it's closer to a core. And the way this is quantified is if you just measure the slope of the density profiles, you just plot density versus radius, you can measure what is the power law slope of that thing if you just fit a power law to it. And so NFW cusps have a power law slope in the center of -1.5, but a core would mean a flat density profile. And a lot of these galaxies with enormous crazy error bars look like they have not quite cusps, but again, the error bars are large. And if you go out and measure non-dwarf spheroidal galaxies, if you go out and measure spiral galaxies that are far away, they really don't look like they have cores. But there's good reason for that. I mean, like, that doesn't mean that CDM is wrong, because there's stuff in galaxies other than dark matter. There are stars in galaxies and people and politicians. And so they tend to mess things up. And so what happens is the baryonic feedback inside of these dwarf galaxies can rearrange the mass distribution. And in particular, if you have violent enough supernova explosions that can rapidly push around gas, especially more rapid than the relaxation time of the galaxy, then you can actually push around dark matter. And so you can transmute a cusp into a core. And so that's kind of the idea, is that baryonic feedback can transmute a cusp into a core. But it can only do it if you have enough baryons. You have to have enough supernova to push around the dark matter. And for the little tiny dwarf galaxies, especially this little one, Bootes 1, this ultra-faint dwarf galaxy, it is not expected to have ever had enough supernova to push around that much dark matter. These ultra-faint dwarf galaxies are really, really dark matter dominated. Their mass to light ratios are incredibly high. And so their baryons are just too wimpy. It's not that individual supernova are too wimpy, but they're not enough of them to push the dark matter into from a cusp to a core. You okay? Okay. So it could be that the baryonic feedback is naturally explained with the cusp versus cores, but we actually have to go out and measure what it is. And so these are predictions of what PFS can hopefully do for measuring cusp versus cores. Now, it could be that we do find that the dwarf galaxies actually truly are cored and not cuspy. And that would, especially for these lower mass galaxies, point to some non-standard physics. So there's all these interesting models of dark matter, the coolest being fuzzy dark matter. Fuzzy dark matter posits that the dark matter particle is so light that its de Broglie wavelength is a kiloparsec. And so it actually experiences quantum mechanical wave function interference effects on a galaxy scale level. And therefore, you don't get this cuspy profile. You would get a totally different weird shape profile. And so how we're going to do that, we're going to go out and measure the line of sight velocity distributions for these galaxies in an attempt to actually constrain what the dark matter profile is. Now, this is a whole industry that has a lot of complications in it. And it has a special number of complications in it if the only component of the velocity that you're measuring is the line of sight velocity. That's what a spectrograph can do. It can measure the line of sight velocity. What we're not measuring is the tangential velocity on the sky. And the stars that we're looking at are too faint for Gaia, I'm sorry to say. So we're not going to be able to know anything about the tangential component for most of the stars that we're observing. We only have the line of sight velocities. And so it so happens that if you're truly measuring not just the velocity dispersion, but the full line of sight velocity profile, and you have enough stars, and enough, I mean thousands, then you have a hope of breaking all these degeneracies, for example, the one that between the slope of the dark matter profile and the velocity anisotropy. So if you remember your Binnian Fermat, you know that there's this thing called the velocity ellipsoid, and it has a tangential velocity component, and there's this radial velocity component, and there's this thing called the velocity anisotropy. Well, that velocity anisotropy really screws with your ability to measure the slope of the inner profile. But if you have enough stars and you have clever enough modeling, you should be able to break that degeneracy. So that's what PFS aims to do. We aim to be able to measure the slopes of the inner profiles of these dwarf galaxies to try to tease out what they actually are, to say something about the nature of dark matter. Now, Laszlo, who I mentioned on the first slide, is working very hard, actually has already produced a radial velocity pipeline, and he's made estimates of what he thinks the radial velocity precision is. Now, what I'm showing you here is the random errors in radial velocity, not the systematic errors in radial velocity. So if there's systematic errors in wavelength calibration, and they're going to impose some kind of floor, which we expect to be about 1 kilometer per second. But as a function of I magnitude, here's the errors that we expect. And in particular, I want to point out, it's the green line that you're looking at, which is the radial velocities would get from combining the blue arm with the medium resolution arm. And for M31, where we're going to observe for 5 hours, we expect around 1 kilometer per second velocity errors, all the way out to 20-second magnitude in the I band. That's pretty impressive. And so this is how we have a hope of being able to use the dynamics that we get from PFS to be able to constrain these things. Now, another thing that we can do with dwarf galaxies, in addition to dynamics, is their chemistry. We can measure the metallicities of stars. We can measure detailed abundance ratios in stars. And one of the reasons that PFS is so interesting is, as I mentioned, there's these radial metallicity gradients in dwarf galaxies. So there's plenty of studies on these radial metallicity gradients. I am selfishly pointing out my own studies. Now, these studies that I did with Deimos do not go out very far at all. And so to show you what I mean, these radial gradients that I observed in dwarf galaxies with Deimos, the Deimos field of view is smaller than that little radius right there. That little radius right there is the half-light radius of these dwarf galaxies. And this dashed line is the tidal radius of these dwarf galaxies, the putative tidal radius. What that means, that's the point at which a star should be roughly no longer bound to the dwarf galaxy, but outside of it, the star is now under the gravitational influence of the Milky Way. And so stars that wander outside of the tidal, this isn't strictly true, but roughly the stars that wander outside the tidal radius can be stripped off of the galaxy and form these tidal streams. Now you notice that our PFS pointings are intentionally outside of the tidal radius. We're going to be looking for these extra tidal stars. And so there really are chances for us to be able to find these stars that live outside of the tidal radius. Now, another thing that's the bugaboo of this work is binary stars. So we're trying to use the velocities of stars to measure something about the mass profile of these galaxies. But the thing is, stars are not single stars always. Sometimes they're in fact, very often they're in binary systems. And their velocities, as we measure them from the Earth, aren't necessarily probing just the potential of the galaxy. They're probing the potential of the binary system in which they live. And so we have to be able to figure out, at least in a statistical sense, how many of these stars are in binaries and how much to trust their velocities. So all of these pointings of PFS that are colored in red are pointings that we're going to go back and reobserve to see if the velocities of the stars have changed. And we can pipe that information into a model that estimates the binary fraction of these systems and then backs out the true intrinsic mass profile of the galaxies after correcting for the binary effect. And so this is how many pointings we're doing in each of the 7 dwarf galaxies that we're observing. And so the second epoch pointings, those are the ones within the tidal radius you can see on the right side there. Now that we have all these stars out at large radius, we can measure, first of all, the velocity distribution, but also they look for these radial gradients in metallicity and in abundances. How do we measure abundances? Well, this started with work from my former PhD student, Ivana Scala, who then handed it off to Roman Gerasimov. Now, Roman has written this really awesome code that he calls, not very creatively, ChemFit. So it fits for the chemistry of stars. But the 2 impressive parts about ChemFit is that he's developed a very large grid of first principles synthetic spectra. But unlike most such grids, all of the stellar atmospheres are fully self-consistent with the abundances of the spectra. So it's the most precise that you can get from LTE models of stellar spectra. They're all self-consistent with each other. They're all made with Synthi, which is a Fortran code written by Bob Carruth. It actually introduces some NLTE corrections to certain absorption lines. It's a really impressive grid, and it's accompanied by a fitter that maximizes the likelihood that the observed PFS spectra, or actually whatever spectra you decide to feed to it, are matching to the synthetic spectra. And so the ChemFit fits to a demo spectra shown here. This is one of the more complicated parts of a spectrum, and you can see that ChemFit's doing a pretty good job of reproducing the abundances. And to show you how precise these ChemFit results can be, this is results from a globular cluster, M13. The brightest, most highest signal to noise stars are highlighted in red, and they have a very, very tight clustering in metallicity and alpha to iron space. And so what that indicates is that the systematic errors and the random errors, if you have high enough signal to noise, are very, very small if you put enough physics into your grid of chemical evolution models. I'll just skip that in the interest of time. We'll also skip that in the interest of time. So I also want to point out another very exciting science case that I briefly mentioned, which is M31. And so with M31, we're going to be able to measure one of the most important questions that have been looked at in the Milky Way in the last decade, which is this thing known as the alpha to iron bimodality. So the Milky Way has a multitude of different components associated with it. And as I'll show you in a bit, they're chemically quite complex. And a big question is, how unique is the Milky Way? How much can we learn from looking at our nearest neighbor galaxy about how unique the Milky Way is? What are the things that are in the Milky Way that are different in Andromeda, and what are the things that are not so different? So with PFS, we're going to be looking at 42 different pointings across the face of the Andromeda galaxy. This is the part of the Andromeda galaxy that you can see. So Julianne is here. So if I'm going to point out where the fat footprint is, it's roughly there. That's about right, Julianne? A bit smaller than that. So like this is the fat footprint for Andromeda.
It's in the black circle.
It's in here. Okay. All right. So that's the fat footprint for Andromeda.
And we have the other half of it.
That's right. There's fat is fatter, right?
Fast.
Fast, excuse me. Fast. Okay. I can't keep up. So fast is over here. So fat is here, fast is over here. The PFS footprint is much bigger than that because it's a ground-based telescope, the prime focus of an 8-meter telescope. And we have 42 pointings. In addition, we're also looking at the satellite, the large satellite of Andromeda, M33, or the Triangulum galaxy. So we have 7 pointings in there as well. Now, the problem with trying to find members of the halo of Andromeda, especially over here, is that the Milky Way lives over there. And so galactic latitude is about 20 degrees right here. This is a line of constant galactic latitude, about 20 degrees. There's a lot of contamination. Remember what I said, whenever you look outside of the Milky Way, you have to look through the Milky Way? When I'm looking at the Andromeda galaxy, there's all this stuff in the way, especially over in the top right region. And so I don't want to spend my precious PFS fibers looking at the Milky Way trash. I want to look at the good stuff. I want to look at the red giants that are members of Andromeda. And the way that I do that is, the way that we do that is pre-imaging in this narrowband filter called NB515. The NB515 filter is centered on the magnesium B triplet, which is very, very sensitive to the pressure or the surface gravity in the stellar atmosphere. The reason is that the magnesium triplet is pressure broadened. So for stars that have like the surface gravity of the sun, for example, the magnesium triplet is pretty fat in the sun. But red giants are big and puffy. They have large radii. Surface gravity is gm over r squared. And so for big, puffy red giants, they have very narrow magnesium triplets because they're not pressure broadened. And so their equivalent widths are a lot lower than in dwarf stars. And so this narrow band filter sorts out dwarfs versus giants in this color space. And that's good because this is what the color magnitude space looks like. The color magnitude space, this is the red giant branch, but it's completely overwhelmed by all of this stuff out here. This stuff out here is foreground dwarfs in the Milky Way coming in multiple different tracks. And so in order for us not to spend our precious fibers on those foreground dwarfs and instead look at the stuff that's highlighted in red, we pick stars from this region of the color diagram, which indicates that those things truly are giants. And if they have this magnitude, if they're 22nd magnitude and is truly a giant star, it's not in the Milky Way. It's in Andromeda. It's got to be far away. So this is the actual pointing that we're going to be doing in Andromeda. And the reason I'm showing this is that we just designed this like this week. So our observations of M31 start on September 12th, I think, which is next Friday. And so we're just by the seat of our pants getting our targeting done. The color coding here corresponds to the priority of stars that we want to observe. So the orange has the highest priority. Those stars have been selected with the narrowband imaging to be true red giants. The brown stars are the ones that are not red giants. And so you notice that even in this part that looks like it should be part of the red giant branch, there's still some brown stars hidden behind here. Those are the stars that have lower priority. So you notice that in the densest regions of the galaxy, we can afford to just target the high priority for sure giants. And then as you go to the less dense parts of the galaxy, they get to be less and less members of Andromeda, and we have more and more non-member stars targeted. I have to skip that in the interest of time. And so one of the main science cases we have for Andromeda is to see how similar is it to the Milky Way, especially in this alpha to iron diagram. And so one of the reasons I want to look at this is that this plot shows the alpha to iron ratios of the Milky Way. So you notice there's this high alpha iron track and a low alpha iron track, and this is in the disk of the Milky Way. But preliminary observations with JWST and M31 look like this. There doesn't seem to be any bimodality in this particular field of JWST. Now I say this particular field of JWST because I want to point out this little square to scale is the JWST field. And that's exactly where it is, where it was observed. So this is the entire Milky Way with a whole bunch of biases associated with it. But this is an incredibly tiny section, a very specific section of the M31 disk. And so I believe that that tiny little section of M31 doesn't show an alpha iron bimodality like the Milky Way does. But that doesn't mean that the entire structure of M31 doesn't show alpha iron bimodality. In fact, if you look in the planetary nebula, which is what you see over here, so there's these high extinction planetary nebula and the low extinction planetary nebula. The low extinction planetary nebula are the old ones, and the high extinction planetary nebula are the young ones. If you look at the high extinction versus the low extinction planetary nebula, they have a very strong gradient with what they look like as a function of radius in Andromeda. So now I'm going to scroll through different radii. And so here is the high extinction, the young planetary nebula between 2 and 14 kiloparsecs, between 14 and 18 kiloparsecs, and in between 18 and 30 kiloparsecs. So as you go out in the galaxy, at least the young population of planetary nebula has this sweeping of the alpha to iron ratio, which is telling you something about the rate of star formation. It's telling you something about the how the disk of Andromeda formed. And so it didn't look like it from these pointings that we're going to be observing the disk of Andromeda, but we will eventually. So we're not observing the disk this year, but we will eventually have a bunch of pointings here as well. We'll be able to answer this question. Finally, we're also looking at the Milky Way. So Kirby is heavily involved in this. And so what she can do and what the whole Milky Way group within the Galactic Archaeology group within PFS can do is use things like the metallicity versus the ages of the stars to answer questions about whether the accretion came from a young event or an old event. And the way that we can measure ages of stars is that we specifically targeted main sequence turnoff stars in the outer disk of the Milky Way and also in the nearby halo of the Milky Way. And with these Milky Way, with the main sequence turnoff stars, you have a good sense of what their age is because they're turnoff stars. And so you can tell the difference between an accretion event that happened, say, 3.8 billion years ago. So this is a simulation that looks, it has a different age metallicity relation than an accretion event that happened longer ago. And so with that kind of information, you'll be able to tease out different formation scenarios for the Milky Way. Now we're targeting very specific sight lines in the Milky Way. And the reason is that we're measuring line of sight radial velocities. So if we're looking at stars that are pointed away from the galactic center, we know that our line of sight radial velocities also correspond to galactic centric radial velocities, V capital R. So the line of sight radial velocities correspond to the galactocentric radial velocities. But we're also looking at a galactic longitude of 90 degrees, where the line of sight radial velocities more closely correspond not to the radial, but the phi component of the radial velocities. And so that way, by choosing our directions of sight deliberatively, we'll be able to know more closely what component of the dynamics of the Milky Way we're looking at. Okay, so in the last 10 minutes, I want to tell you about the actual data that we've acquired. So I mentioned that in March, we started our 6-year exploration of galactic archaeology with PFS. And we observed 2 dwarf galaxies, and we observed a few fields in the Milky Way. So I'm just going to show you the results of those 2 dwarf galaxies just from the March observations. So this is what our pointings for Ursa Minor. This is one of the smaller dwarf galaxies that we're going to be looking at. This is what the pointings for Ursa Minor are going to look like over the full 6-year survey. This is what the pointings for Ursa Minor look like that we obtained in March. So we're starting off with just these 2 pointings. And the color coding here is given by the priority. So this, how securely we thought the stars were red giant members of Ursa Minor based on that narrowband pre-selection. This is what the color magnitude diagram of all those stars looks like. This is what the color diagram of all those stars look like. So you notice that the lighter colored stars are the ones that have more negative NB515 minus G colors, which indicates that they really are giant stars. Now, I want to point out how many stars this is. This is about 4,000 stars that we obtained in just about 6 hours of observation. 4,000 stars in 6 hours of observation. Now, not all of those are members, but still, this is an incredible volume of data that's coming in for ground-based spectroscopy. This is what the quality of spectra look like, and it's really impressive. When I saw this, I actually lost my breath a little bit. This is one of the brightest stars that we observed in Ursa Minor, and this is sort of a middling brightness star that we observed in Ursa Minor. I'm not showing you the faintest stars because there's still issues with the data reduction. And so there's some wavelength calibration issues that are especially pesky for the fainter stars. So this is actually the faintest star for which we've measured an abundance so far. We'll be able to measure abundances for much, much fainter stars. But because of the issues with the data reduction that are still being worked out, this is the faintest star for which we're measuring an abundance. The black line shows you the ChemFit synthetics model spectra. That's the best fit to the observed spectra. And the blue dots are showing you, with error bars, what the flux measured by PFS is. This is what the redder part of the blue arm looks like. This is what the medium resolution channel looks like for PFS. So you can see the calcium triplet. The reason that we chose medium resolution in the red arm is specifically because you have these 3 spikes in the spectrum, the calcium triplet, which are really good for measuring radial velocities. You also notice that there's some reduction issues here. So like this, if you're really used to looking at spectra, this is O2 in the Earth's atmosphere. This is molecular oxygen in the Earth's atmosphere that's been over subtracted in the spectra. So we're still in the young phases of this survey, and we're still dealing with some of these reduction issues. And also, really impressively, especially for a fiber spectrograph, this is the bluest part of the blue channel. Now, we don't even bother to try to fit the spectra bluer to 4,000 angstroms, so you can see the model just wanders away from the spectra. But this is the calcium H and K lines. And if you know anything about fibers, they're really bad at transmitting blue light, especially if your fiber is 80 meters long. But nonetheless, you can still see calcium H and K in this 20th magnitude star. So I was really impressed when I saw it. I was like, wow, I did not expect to see calcium H and K. So this is what the Ursa Minor looks like in surface gravity versus velocity space. And the way we know if we got a member of Ursa Minor is if it's at the correct radial velocity, for one thing. But also, I want to point out that this is the ChemFit measurements of surface gravity from the spectra alone. When in this particular iteration of ChemFit, we didn't tell the software what the magnitude of the star was. We only gave it the spectrum. And from the shapes and strengths of the absorption lines, it inferred what the surface gravity is. And if I show you what the surface gravity is, if I color code now, not by the priority of the star, but by the surface gravity, what you see is that in the color magnitude diagram, the stars with the lowest surface gravity are at the top of the red giant branch, and with the highest surface gravity are at the bottom of the red giant branch, exactly like it should be. I can't tell you how difficult it is to measure surface gravity from a low resolution spectrum. This was really impressive when I saw it. You see all this stuff here that looks like it's at high surface gravity. That's because those are foreground dwarfs at high surface gravity. So we kind of knew those weren't going to be members, but ChemFit properly told us that no, indeed, those aren't members. Those are foreground dwarfs in the Milky Way. This is the metallicity distribution that we infer for the dwarf galaxy. Now, I want to point out that out of those 4,000 stars, we've only measured abundances for 245 of them. Again, that's because we're dealing with data reduction issues. I expect this number to increase by about a factor of 5 at least. And that's just for the first 2 pointings of the galaxy. We can also measure alpha to iron ratios, and eventually we're going to be measuring individual abundances of things other than iron. I say M over H here because what ChemFit measures is really a bulk metallicity, not just an iron abundance. It's the bulk metallicity of the star. And you can see very nicely a plateau in the alpha to iron ratio and then a smooth drop off, which is like the textbook chemical evolution that you'd expect for a dwarf galaxy. You have the core collapse supernova producing a constant alpha to iron ratio, and then the type 1a supernova turn on and produce just iron, and then the alpha to iron ratio falls off. I want to compare this to sort of my life's work. And so this is, in red, you're looking at my previous measurements with Keck Deimos. Again, this number is going to increase by a factor of 5 when we get our act together with the software. Over like 5 years of acquiring data in Ursa Minor with Deimos, I got 230 stars. In 6 hours, we got 245 stars without even having the reduction correct. And so in a couple of nights on PFS, completely made obsolete everything I've ever done with Ursa Minor. And I couldn't be happier about it. Also, the measurements for alpha to iron ratio come out a lot better. I never really liked my measurements from Deimos because I always got these really high alpha to iron ratios, which just didn't exist in the Milky Way. And I always doubted whether or not they're real. And the reason is that I've been trying to measure alpha abundances just from a narrow region in the red part of, or actually the near infrared part of the spectrum, where there aren't a lot of good alpha absorption lines to use. With PFS and its wide wavelength range, especially towards the blue, you can really cut down on all this fuzz and really recover the true alpha abundances for these stars. We've done the same thing in Draco. So Ursa Minor isn't the only galaxy that we observed in March. We also observed this Draco, and similar story there. So I want to wrap up now. In summary, the PFS Galactic Archaeology Survey is going to address these 3 main science cases: the dwarf galaxies, M31 and Triangulum, in the outer Milky Way. Our 6-year mission has already begun. It's going to last until 2031, and the spectra look great. And so I'm kind of showing these spectra a little bit prematurely because there's still some reduction issues to work out, but I was too excited not to show some real data to you. So thanks very much for your attention.
Okay, we have 6 minutes for questions. If anyone would like, okay, Julianne.
So, your abundances are very nice. Do you take those error bars seriously?
No,
Well,
no.
Well, no,
Thank
but like, I mean, if you, but let's for, okay, right, let's go back for a moment and take that seriously. Like, there's things that are not on that relationship. Does that interest you? Like,
Yes, they do interest me, but again, we don't trust the reductions yet. And so I didn't put a lot of time into investigating whether or not these things were even actually members.
right, you're on the other side, right? Like there's that and then down below.
Yeah, I mean, I don't even know if those things are members. And if they're not, then yeah. So they could be real, in which case they'd be very exciting. But this is very, very, very preliminary. And so I didn't invest a lot
Well,
of time.
thank you for sharing it.
Okay. But yeah, you make a really good point, Julian. Like the error bars here are really just the random error bars. So what that means is that it's just based on the likelihood function. And if the signal to noise is very high, you have a very, very narrow likelihood function. We're going to estimate the systematic uncertainties and add those into the error bars when we have good enough data to do that. But right now, the error bars are really just a reflection of the signal to noise of the spectrum, not the true error of the spectrum.
Lucia.
Oh, wow. Okay, I don't do stars, but I think question I think is related. I noticed on this plot, and I think one on 30, that some of the points end up on exactly the same alpha, like Y point.
Yeah.
Where is that coming from? Is that like something that, like in this one specifically?
Yeah, good eye. So yeah, there are these kind of, Roman calls these magnetic attractors. And the reason is because ChemFit is based on a spectral grid. It's not quite an even spectral grid, but it's fairly even. And what you're looking at is the grid points in surface gravity. Again, surface gravity is really hard to measure from low resolution spectra. And so the likelihood functions aren't super sharp. And so what happens is if you're doing linear interpolations between your spectra like we are currently, the likelihood functions have not a discontinuity in the likelihood themselves, but they have a discontinuity in their derivatives. And what that can cause to happen is that sometimes the likelihood will stick to the grid points at those discontinuities. And so what you're seeing is a reflection of the structure of our spectral grid.
Ida.
So do we expect major galaxies to have this like alpha to iron bimodality that we see in our own galaxy?
Oh, that's a good question. Yeah, it depends on what you think the alpha to iron bimodality comes from. But if it's, I feel like I'm not really the person to be talking about with Rosie sitting here. But if you think that it has to do with the unique accretion history of the Milky Way, then no. I mean, if Andromeda has a different accretion history, it should have a different alpha to iron bimodality. I'm sorry, it have a different alpha to iron distribution. It may not even have a bimodality.
Neil.
Yes, I understand the telescope time is limited, but is there a reason you're staying away from globular clusters? About those.
That's a great question. And in fact, PFS itself is not staying away from globular clusters. So what I just presented was the Subaru strategic program for the 360 nights. But you can also, if you have access to Subaru, apply for geotime or PI time on the telescope. And there are multiple PI programs that have been looking at globular clusters already. So yeah, you can certainly use it to look at globular clusters.
And technically we did.
Technically we did during our commissioning runs, yeah. Not even technically, we actually did look at globular clusters during commissioning.
What the difference is technically.
One last question from Adrian.
This is a quick one, I guess. And since you called me out on streams, I have to ask, how did you pick the particular streams that you?
I didn't.
Because those are some pretty.
I didn't.
Okay. Obscure ones, let's say. Okay.
I didn't. I'm going to defer to our Japanese collaborators on that one. Sorry. I don't know if you want to say anything. Okay.
Decline to comment.
Okay.